Long before a commercial vessel cuts through the open ocean, its life begins at coastal multi-purpose shipyards. Naval architects design the hull to slip efficiently through the water, but the vessel only actually moves because of a small, unseen group of engineering professionals working below the waterline. At the core is the main engine. These two-stroke marine diesels stand over 42 feet tall, span 4 stories, and weigh over 2,000 tons. They exist in a harsh environment. The engine room operates under extreme thermodynamic pressures and experiences drastic temperature shifts, making it the loudest and hottest space on the ship. Because of its sheer size and immense torque, this powerhouse turns the massive propeller directly. There is no reduction gearbox between the combustion chambers and the ocean. The physical reality of the floor is brutal. The heat is stifling, the noise is deafening, and the heavy machinery pulses with constant vibration. Harnessing this volatile energy requires highly rigid procedural discipline. It relies entirely on a strict human hierarchy operating in synchronization. Steps away from the deafening heat of the engine floor lies the engine control room. It is an enclosed, air-conditioned sanctuary that provides a stark physical contrast to the heavy machinery outside. Every vibration and temperature shift outside is distilled here into clinical digital readouts, monitored across a wall of screens and switchboards. Directing this space is the chief engineer, acting as the ultimate systems architect at the center of the controlled chaos. They carry the direct responsibility for the operation and maintenance of every single piece of electrical and mechanical equipment on board. The technical demands of this role are severe. Due to a global shortage of senior marine engineers capable of doing this work, chief engineers command a level of authority and often a salary equal to that of the ship's captain. The control room represents a distinct boundary. It is the exact point where raw thermodynamic power is tamed, calculated, and converted into safe propulsion. Modern vessels often operate under a UMS, or Unattended Machinery Space Notation. This certification technically allows a 100,000-ton industrial facility to run completely autonomously overnight. This schematic shows data flowing into a central node. When locked down for the night, a vast network of sensors continuously monitors the unattended machinery. Yet this setup is fragile. A single mechanical failure immediately disrupts the entire network. If a pressure drops at 3 a.m., the duty engineer sleeping in their cabin relies entirely on bulkhead alarm repeaters to jolt them awake and notify them of the fault. The risks are high. A fuel pump seizure or a suddenly cracked cylinder liner requires immediate, physical human intervention. If these failures are not addressed instantly, the main engine shuts down, leaving the vessel completely dead in the water and at the mercy of the ocean's currents. This autonomous period is only possible because the engineering team spent their waking hours ensuring every pump and circuit was perfectly calibrated for the night. In the engine room, waiting for machinery to break before fixing it is a guaranteed route to catastrophe. Reactive maintenance is simply not an option. Engineers instead rely on the Planned Maintenance System, or PMS. This digital tool dictates strict, non-negotiable service intervals for every single component on board. The hierarchy ensures these intervals are met. The second engineer delegates tasks, third and fourth engineers handle fuel, and the electrotechnical officer manages automation. Supporting them are the ratings, motormen and oilers who walk the floor to perform manual rounds, physically checking valves and ensuring the heavy rotating machinery remains lubricated. The actual maintenance is slow and meticulous. Every filter, valve, and piston is routinely stripped, cleaned, and reassembled to exact specifications. Every turn of a wrench generates a permanent, auditable record, required by international classification societies to keep the vessel certified. This careful, methodical routine stands in stark contrast to the high adrenaline necessity of emergency readiness. Operating thousands of miles from land, the crew cannot call for backup. If a fire breaks out, the engineers must immediately act as their own fully equipped fire department and rescue squad. Engine room survival depends on absolute procedural discipline. Proactive maintenance is a strict life-or-death requirement. Reaching the rank of chief engineer requires a grueling 8 to 12 years of continuous academic study and documented sea service. Cadets undergo intensive theoretical training in thermodynamics and applied mechanics, explicitly structured to meet global STCW conventions. This rigorous foundation is necessary because the chief engineer enforces the heavy mandate of international maritime law, specifically governing environmental compliance and emissions. Today's engine rooms are packed with complex green technologies, from ballast water treatment systems to advanced LNG dual-fuel engines, all under the chief's command. This chart maps thermodynamic efficiency against emissions. Modern turbochargers capture exhaust heat to boost engine power by 200%, driving carbon emissions down. The data is so robust that classification societies trust chief engineers to self-certify this highly efficient equipment. The engineering team constantly balances the vessel's raw power output against strict environmental metrics, like the carbon intensity indicator. The modern rank requires the engineer to mathematically and legally prove the vessel's right to operate in a decarbonizing world. As the vessel prepares for its final arrival in port, the physical stakes of crossing a vast ocean come into focus. It takes rare psychological resilience to live in tight isolation for months, working shoulder to shoulder with high-voltage systems and millions of gallons of combustible fuel. This chart breaks down the root causes of maritime accidents. Industry data shows that over 80% originate directly from failures in the main diesel engines. That statistic highlights exactly why human oversight remains an absolute necessity. Expert vigilance prevents those failures from occurring. Once the ship is safely secured at the berth, the engine telegraph rings from the bridge, executing the final sequence of commands to stop propulsion. Fuel valves are closed, system pressures drop, and the massive steel propeller shaft slowly comes to a halt. The mechanical heart finally rests. But for the engineers, the vital work of auditing, inspecting, and repairing never truly stops, ensuring the global supply chain keeps moving.